Okay, great. Yeah, thanks everyone, and particularly thanks to the organizers for this opportunity, and in particular for accommodating this talk over Zoom. And I'm really sorry for not being there in person. So I'm Srini Raghunathan, and I'm going to talk about constraining the epoch of reionization using CMB as a backlight. And in particular, I'll be highlighting this recent result from the South Pole Telescope collaboration, which is constraining reionization using the tri-spectrum of the kinematic SZ effect. I will go into more details in the following slides. Okay, so I think we have heard enough about this, so I'll just mention this briefly. So the standard model of cosmology is that we have cosmic inflation at the beginning, followed by the Big Bang. And structures in our universe, they grow via hierarchical clustering. Gravity is really well explained by general relativity. And the universe that we live is spatially flat. And besides besides normal baryons, we also have dark matter and dark energy. And we have pretty strong evidence for pretty much all of these things except inflation. And that is basically the one of the major science drivers for the upcoming CMB experiments like Simon's Observatory and CMB-S4. So in this talk, I'm going to focus on this window, which is redshift between 8 and something around 12, where our universe went through this period called cosmic reionization. So I will mention about how to use the cosmic microwave background to study this reionization process. Okay, so before going into this, I just want to briefly introduce what CMB is and why it is useful in measuring several things. So cosmic microwave background is the remnant radiation from the Big Bang. It was predicted in 1940s and accidentally observed 20 years later by Penzias and Wilson. So discovery of CMB, as you might all know, is one of the strongest evidence supporting the Big Bang model of the universe. Okay, so initially the universe was extremely hot. And then it took around 400,000 years for the universe to become neutral enough. So this free streaming, so the CMB photons could actually free stream towards us. And then later, as universe expanded and further cooled and started forming structures, so we have first stars and galaxies. So these first stars and galaxies are emitting ultraviolet photons, and these photons are reionizing the universe. Okay, so the CMB is extremely homogeneous and isotropic. So it's nearly black body radiation with temperature around 2.7 Kelvin. And CMB is also partially polarized due to Thomson scattering at the time of recombination. The other most important detail for this particular talk is that CMB is the most distant light that we can ever observe, and it's present in all directions. So what happens is that CMB photons are free streaming towards us from the surface of flash scattering, and they actually interact with everything that we know in the universe. Okay, so basically they interact with galaxies, structures, and everything that we know in the universe. And this interaction leads to secondary anisotropies in the CMB, which is an excellent probe of reionization, structure formation, and several other things. So how do we actually probe reionization using CMB as a backlight? There are multiple ways. And the first here is the kinematic SZ, which is the main theme of my talk. So I'll discuss more about that in the next few slides. But then there are other ways. So one of the way is, so the CMB photons are going through these dense clouds, which are optically thick, and as a result, there is an attenuation that happens to the power. So basically, we have suppression of power on all scales. Unfortunately, though, this suppression is extremely degenerate with the amplitude of the power spectrum. So it's very hard to understand reionization just using this power suppression. The other thing that we can do is measure this bump on very, very large scales in the polarization map. So it's called the EE bump. So it's a bump that is around L of 10, so multipole of 10. So that roughly corresponds to the size of the universe at the time of reionization, when we have additional polarization being generated due to these additional free electrons that we have in the universe at the time of reionization. So this has been done. So Planck has observed this, WMAP has observed this. So the problem with this particular measurement is that it's on very, very large scale, and as a result, it's really hard to access this particular signal from ground because of sample variance. The other important detail about this is that this particular bump is not really sensitive to reionization histories. And here is a really nice plot from Planck. So where on the left side, showing the ionization fraction of the universe as a function of redshift for different models of reionization. And on the right side, showing the E mode bump that comes because of all of these reionization histories. And as you can see, all these different colored curves are sitting on top of each other. So it's very hard to use the E mode bump to understand how reionization actually happened in the universe. There are also other fainter signals, and I'm not going to go into detail about those things. So now let us focus on KSE. So what is KSE? So this is a Doppler boosting of CMB photons. So this is a secondary anisotropy that's produced because of free electrons that we have in the universe, but particularly these free electrons are in motion. So there are two sources of the kinematic Z signal. So one is a high redshift source. So these are basically patchy reionization bubbles caught up in the bulk velocity flow in the universe. And then there is also small scale matter inhomogeneities that happens later in the universe, the low redshift component. So this low redshift component can be easily observed by cross-correlating CMB maps with galaxy surveys. And this has been done by pretty much all the major surveys like ACT, SPT, and Planck. However, understanding this reionization signal is hard. So let me go into a little bit more in detail. So what exactly are these? So reionization is the period when first stars and galaxies reionize the hydrogen in the universe. So that is a later phase where helium reionizes in the universe. But I'm going to focus only on hydrogen reionization here. So this is due to energetic ultraviolet photons from first stars and galaxies. So universe was neutral after recombination, but then these ultraviolet photons from stars and galaxies are basically kicking an electron out from these neutral atoms, and that's how universe becomes reionized. So this process, so this epoch is the epoch of reionization, and it's expected to be a patchy process. So how do we actually understand reionization using KSE? So one natural thing to do would be to just take the power spectrum of our map. So we observe the CMB map, right? So the CMB map that we observe as contributions from all these four components. So we have the desired KSE signal. We also have lens CMB. We have instrumental noise. We have atmospheric noise, but we also have astrophysical foregrounds. So we combine all these things. So that's basically what we observe. And then we take the power spectrum of this map, and we fit for all these components. And then we say finally infer whatever is left out will be KSE. So this has been done. This has been done by with SPD data in particular. So we have 3 to 5 sigma evidence for KSE. However, using the 3 to 5 sigma evidence is still very hard to actually understand something about reionization. The reason for that is because of all of these things. So when we take the power spectrum of the map, so like I said, we have contributions from all these other signals. In particular, these astrophysical foregrounds are really hard to model. And when I say astrophysical foregrounds, so these are basically thermal Z signal. This is signal from dusty galaxies and signal from quasars and radio galaxies. So some of these are easy to model, but some of these are extremely hard. In particular, the signal coming from cosmic infrared background is very, very hard. And as a result, if our modeling for the CIB is wrong, our inference for KSE is going to be wrong. And so we have to be very careful in the way we model this thing.
Srini, you have 5 more minutes, please. Thanks.
Okay, great. Yeah, thanks. And even if we ignore all of these foregrounds, we finally observe this KSE signal. But like I said, this KSE signal has contributions from 2 things. One is the early time and the other is late time. And modeling this late time, again, is very, very hard. So saying something about reionization using the 2 point of the KSE is a little bit hard. So what was proposed back in 2016 by these papers by Smith and Ferraro, Kendrick Smith and Simone Ferraro, is that instead of looking for the power spectrum, we can actually look for the 4-point function or the tri-spectrum. So KSE does not have bispectrum because it just cancels out. So basically what this is basically looking for non-Gaussianities in the KSE signal. And this is basically just a large scale modulation of small scale clustering of electrons. So, okay, so we have electrons sitting in different locations in the universe at the time of reionization. But then there is this bulk velocity flow, which is basically modulating all of this signal. So what we can do is we can build an optimal quadratic estimator, which is simply take our CMB map, filter it for the characteristic scale, and then just square it. It's very similar to CMB lensing. And we tried this with the South Pole telescope. So what is South Pole telescope? So South Pole telescope is is a 10-meter diameter telescope at the geographic South Pole, observing the CMB in 3 bands, 90 gigahertz, 150 gigahertz, and 220 gigahertz. So what we did is we looked for the signal. In particular, we chose a patch that's only 100 square degrees wide. So the area is basically 100 square degrees. And the reason we chose this patch is because we have data from 3 generations of South Pole telescope in that particular field. But more importantly, we also have data from Herschel satellite, which is actually a very, very good proxy for signal from the dusty galaxies. So we combine data from all of these instruments, and then we made this measurement. So what you're seeing on the left is basically the map of this KZ signal, and on the right you're seeing the tri-spectrum of the signal. So the green are the data points, and the violins are basically the expectations coming from simulations. In particular, I should say that these simulations do not actually have the reionization KZ in them, which basically tells us that whatever we are seeing here, whatever we are measuring here, is actually not the reionization KZ, but it's actually the residual signals coming from CMB lensing and astrophysical foregrounds. So we try to optimize our measurement so that all of these contributions are low, but they are still present. So we don't measure the KZ 4-point. But what we do with this non-detection is that we actually place upper limits on reionization. Okay. So what you're seeing on this plot, so the green data points are our data. The violins are expectations from sims. Black curve is the mean of all of those simulations. And if you can see here, if we subtract the black curve from the green data points, all of our data points are going to align very well around 0. Okay. So we use this non-detection and we set upper limits. So for example, this is basically the upper limit on 2 parameters for reionization. So the vertical axis is the midpoint. So it's basically the time when the universe was 50% reionized. On the horizontal axis is the duration of this whole reionization process. So as you can see, this is the constraint from KZ 4-point alone. And we actually do not have a very, very strong constraint because these two parameters are very, very degenerate when we just take the 4-point information. However, we do have observations of other things, like for example, from Lyman alpha forest, basically the Gunn-Peterson trough that was observed by multiple groups, which says that the universe must be fully ionized around redshift 5 to 6. So we could use this information now, and we could combine that with the KZ 4-point, and then we end up in this particular really small window because all the other things are excluded by the Gunn-Peterson trough. So when we combine KZ with the Gunn-Peterson trough, we actually set pretty strong constraints on the duration of reionization, so which we get as 4.5. So this is a 2 sigma limit. So we don't detect the KZ 4-point, but we are still able to set constraints on reionization using this non-detection. The other important thing that I should also highlight here is that this constraint is completely independent of Planck. So if we include Planck into this picture, so Planck is basically this blue dash curve. And you can see that our results are actually pretty consistent with what has been observed by Planck using the low L bump. So we don't have a detection, but we set upper limits, but the future is actually looking really good. So how well we can do in future? So this is a forecast done for SPT, Simons Observatory, and CMBS4 by combining 3 different signals. So on the left panel, we have the KZ power spectrum. On the middle panel, we have the KZ tri-spectrum. And in the right panel, we have the joint constraints from all these things and also Planck. So the horizontal axis is the optical depth. Vertical axis is the duration of reionization. So as you can see, the direction of degeneracy for the 2-point and the 4 points are slightly different. So as a result, when we combine them, we get pretty nice constraints on pretty nice joint constraints on the optical depth and also on the duration of reionization. So you can see we can even actually improve tau when we combine KZ with Planck. So the future is looking good. However, we don't have a detection yet. And that's my summary. So KZ, besides the low reionization bump, is an excellent probe of reionization. In particular, the 4-point function is a really good way to mitigate modeling difficulties due to late time KZ signal. And recently with SPT data, we set the first constraints, upper limit on reionization. But the future, both for SPT, Simons Observatory, and CMBS4 is looking really promising when we combine KZ with other probes of reionization. And I'll stop there, and thank you so much for listening.